All right, so like I was saying, no, today is not an outside day. Because what we're doing today is not relevant outside. No, we're not. And why is this not on the screen? We're in practice. All right, so, yep, let's do this. We'll get through it as fast as we can. What do you want? I already said no. All right, so we're talking about the models of the solar system. What's a model? What's a model?
It's like a model is a scaled down version of something.
Okay, so model's a scaled down version. It's an example of something. So here I have the America's Next Top Model and a Model A. Those are not it. Sorry. There were, what's the model of the solar system?
The Milky Way.
No.
It's the Mr. Winter.
It's when you got the sun and you got the planets. There used to be a different model of the solar system, and that was called the geocentric model.
That was when the Earth was the center.
Where'd you get that information?
Global class.
Global.
I had.
Okay. Yeah, you got it. All right. So from the word geocentric, you should hear in there geo like geology or geo like geography, and then centric. So that is center. So geo is Earth, centric. So for this spot, right after the word geocentric, I want you to tell me Earth is the center. And what that means, so I guess I screwed up the notes. So where it says geocentric model, we need okay, there's just not a lot of room to write. So you can do geocentric model, Earth is the center. Get rid of where it says explains the following. How about that? Yeah. So right on page 14, where it says explain the following, because I said we're skipping around. So geocentric model, the geo, which is the Earth, is the center. Yes. Yeah, we already did if you forgot yesterday. Mm-hmm. Sure.
I'll get you if I'm not too.
Okay. All right, so the geocentric model, this is what they used to believe back in the day. For the record, it is not what we believe anymore. But like we've already talked about, were they complete idiots because of this?
No, I just didn't know.
Right, they just didn't know, and it made sense. Doesn't it look like every day the sun goes around us?
Yeah.
Starts up low, gets high in the sky, goes low. You can only assume it keeps going around the Earth underneath us. That makes sense. Same with the moon. The moon rises, the moon sets. It looks like it goes around us. If they stared at the stars all night long, they would see that it looked like the stars were moving around us. And again, now we have different explanations for all of that. But at the time, they used what they had and they went with it. In addition to it, they add then, and this is probably kind of some of the stuff you talked about in global, they used religion to explain it as well. God made the earth, of course he made us the center of it. So it only all just made sense to them. And I think you guys know that people that started going against this thought, Galileo, Copernicus, you guys know from Global what happened to them? They did eventually die. They didn't actually kill them. But Galileo and Copernicus, they were put under house arrest so that they could not share their teachings with other people. And it wasn't until like recently that the Catholic Church actually said, hey, you know what? We're really sorry about that. We were probably wrong. So it did not explain. So see where it says it did not easily explain the following, then I just have a white space for you to write there.
Yeah.
We just need this one bullet in that white space, so there's no lines there. It didn't explain the movement of the inner and outer planets. They were able to see some of the planets moving without really good telescopes or anything. They were able to see some of the planets, like we can see Mars, we can see Mercury still even today. And I don't have any Kleenex, so paper towels on the wall.
You got my notes?
Yeah. Anyway, those planets don't go around, page 14, Alyssa. They don't go around like the moon and the sun go around us. They kind of go from one spot back to another and back to another. And that's because they're not going around Earth. So it didn't explain that. And then that's when we came up with the heliocentric model of the solar system. Helio, like helium, which by the way is what the sun is made out of. Yeah. I'm not sure which came first, knowing that and naming. I think what they did is they named helium because they had already named the sun Helio, but I'm not sure.
How do they figure out the sun and the outer moon?
So they know the property, so they use observations to make an inference. And now we have higher tech machinery equipment that can look at it and see what it's made out of based on its wavelengths and stuff like that.
So if a solar flare hits us, we all done though, right?
Well, but good news is the solar flare is not going to hit us.
What would we do?
I don't even have an answer for that.
Then I would die.
Yeah, I've always said there should be a class devoted just to what ifs in earth science.
I agree.
This would be one of them.
Well, in movie 2012, we all died.
The day after tomorrow has a lot to do with solar flares as well. Even the core that we were watching, that we started to watch when all those birds were dying, that had to do with the electrons getting to Earth from the sun because the magnetic field around Earth was being deteriorated. So the regions every year, just like they always have a question about altitude of Polaris equals your latitude, they always have at least one question, which is as simple as identifying which model is which. So Geo, just keep in mind, Earth is the center. Helio, sun is the center. By the way, this is the one that is currently being accepted. This is the one we teach all the kindergarten through 6th, 7th, 8th, 9th, 10th grade, that the heliocentric model of the solar system. Sun is the center, everybody else goes around. Now let's move on to the shape of the Earth's orbit. What's an orbit?
Circle. Like a circle.
Yeah, you think it was a circle, right?
Yeah, like,
It's not. Yeah, so it's the path. So it's the path that the Earth takes as it revolves around the sun. Basically, those words are interchangeable. Orbit, revolving. It's just revolutions like the verb. It's the process of going around. While orbit is the path it takes. So it's more like a noun. It's the road that it's taking around the sun. You can say the Earth orbits, then in that case, again, it's a verb, but we don't need to get into this. All of you thought the shape was a circle?
no.
No, because of course not. It's actually, it's slightly elliptical, which means slightly oval. The shape of the Earth's orbit is slightly elliptical, which means oval, with the sun at one foci. So before I go too far, we better establish what a foci is. I'm going to draw some shapes on the board. This first one, you need to pretend is a perfect circle, but I can't do a perfect circle. So pretend that's a perfect circle. What do we even know about the center of a perfect circle? It's the dead smack center. How could you prove it's the dead smack center? Right, so this right here, which is the radius, is the same as this line. And again, mine's not perfect.
So the foci, the one.
So for an oval, is there a dead smack center?
No.
So if I drew a dead smack center like in the middle like you do here, you would see that this radius is much shorter than that one. There's no spot that you could say is the dead smack center. So with ovals, mathematicians have established that basically there are two centers of an oval. And when you do fancy math, you could find them. We're not doing the math to find them. You just need to take my word for it, that ovals have two centers. They are called foci when you're talking about them plural. If you're talking about just one, it's a focus, not important. I will take both versions of the word, so will the regents. So these are called the foci of an oval. They're basically just the centers of an oval. So with the Earth going around the sun is one of these centers. So one of these is the sun, the other one's an imaginary dot in space. You are getting way too complicated in here, but yes, but nothing like that's on the regents. So what is eccentricity? The regents will define the word eccentricity as how out of round an orbit is. Which I think is the stupidest phrase in the world, how out of round. Really, all it means is how oval is the shape. So we're going to be calculating eccentricity. So since we have to calculate it, what do we need?
Calculator.
And
Paper.
what do you need?
Diagram.
How about a formula?
Uh,
Yeah, I asked you to grab, oh, I did not, sorry. Take out your packet and your ESRT. And find the formula for eccentricity.
Found it.
Found it? I'm also gonna deliver you guys a ruler.
Yeah, it's right there.
It is right there. So once you find the formula for eccentricity,
Dang.
no problem. Once you find the formula, go ahead and write it in. And when you get these, there's one for this. Some of the rulers have seen better days. If you could please refrain from adding to any of the graffiti that is on them. I'd appreciate that. So we're gonna actually be calculating this eccentricity. So we have the formula, which is eccentricity is distance between foci divided by the length of the major axis. And then you have an actual oval on the bottom of your page, and we're going to calculate the eccentricity. So eccentricity again. Oh, you were supposed to write it from your reference table.
Oh, where's the?
So distance between two foci, we're gonna start there. Remember, the foci are the centers of the oval. So there are two foci. You need to measure, and this is science class, so we typically measure in. Okay, but in this, because we have rulers in front of us, they're not kilometers, they're. But this, so this is science, so which side do we use? We use the centimeter side. So by the way, some of your rulers will say mm, that stands for metric measurement, which is centimeters, millimeters, etc. Some of you, mine that I have in my hand flat out says centimeters. So we got to measure the distance between the two foci. Go ahead and do that. Go ahead and do that, Logan. I'll give you a personal invitation to it since you missed my last instruction. So here's your ruler. Measure the distance between the two foci.
Oh, already.
So you're going to truly just take your ruler and see how far apart those two centers are. And what do you guys get?
5.
5. So when you measure that distance, I also got 5 centimeters. Now the major axis, what's an axis?
Oh, solar.
Extra wide.
Oh, South Pole. That
Okay,
line.
that's the axis of the earth,
Extra wide.
okay? So in this case, there's several axes, but the major is going to be the biggest, basically the diameter of the oval. And it's because it's the major, it's going to be the biggest one, which it will be, we're measuring how fat the oval is. So go ahead and take your ruler and figure out how fat this oval is.
Like that.
Yep, basically the diameter of the oval. So yes, if it's not, it looks like it's not right on the 10 for me. You do have to estimate, is it 10.1, 10.2? You don't want to just say 10 because that's too far off. However, I think that's what mine was. Oh, no, mine was 10.3. Yours might only be 10.2. The copier does change up some things sometimes. So use whatever you get. And for today, I'll let you use your phones as your calculator today. Go ahead and calculate the eccentricity. So again, eccentricity is the distance between two foci divided by the length of the major axis. So when you plug that in, I got 5 divided by 10.3. Now you guys use 10.2, right?
Mm-hmm.
So let's go with using your calculator. So when we take 10.2 divided by, length of the major axis, which is 5, distance between the two foci, which is 5, right? Distance between two foci was 5, divided by length of the major axis, which you guys got as 10.2. This should be the number you got. I'm going to tell you that on these, they always make you round to the nearest 1,000. What does it mean? 1,000. 1,000. 3 numbers after the decimal. We have tens, hundreds, thousands. The directions for these will almost always tell you to round to the nearest 1,000. So how do we round 4.49019608 to the nearest 1,000? Okay, so we go to the 1,000th, and in this case, it's a 0. We have to decide, does it stay the same or round up? Stays the same because this is just a 1. So in this case, the eccentricity for this would be 0.490. I'll tell you, if you round wrong, you get the whole question wrong. So I just have a quick rounding question. How would we round 0.49972 to the nearest 1,000? Okay, so here's the 1,000. Do we have to round that up or stay the same? Up, but it's a 9. Okay. This is how you would properly round that to the nearest 1,000. And yes, if you did that, you have to include the 2 zeros. If they say 1,000, you have to have those 3 digits. If you don't have the 3 digits, it's wrong, even if they are zeros, which would really stink on the Regents if you got lost a point because of this. I'll tell you, it's a very common place for people to lose points. So make sure you're comfortable rounding. All right, so now that we know how to calculate eccentricity, what do we think the eccentricity of a perfect circle would be? A circle has an eccentricity of. So what do we think? Where are you getting 0 from? Because it's not oval, first of all. So would there be 2 foci in a circle? No, there's only one center of a circle. So what would the distance between the 2 foci be? If there's
0.
There would be 0. And then the length of the major axis would be whatever it is. So we could make up a number and we could say 10 centimeters. And 0 divided by 10 is 0. So 0 is the eccentricity of a perfect circle. What would happen if I made this oval even more ovally? If I made this circle more ovally, it'd be more ovally, more eccentric. And what would happen to the distance between the two foci if I made it more oval? They'd get farther apart. So the biggest eccentricity that we can have, the more oval it is, the more eccentric it is. What do you think the highest eccentricity we could have would be? Because a straight line would actually be, which is not a shape really, but the more oval it would be 0.99. So eccentricity, the least you can have is 0, and the most you could have is 1. And I actually like to demonstrate this. If I showed you this, what shape is this? What's it look like to you? Should look like a circle. I know it's not perfect. What number does it look like? 0. A circle has an eccentricity of 0. Now let me make it more ovally. What number would that be? 1. It'd be like a straight line and look like the number 1. So that's how I like to try and remember that 0 is a circle, and the more oval you make it, the closer it gets to the number 1. You can never have an eccentricity bigger than 1. So the only choices are between 0 and 1. The closer to 0, the more circle. The closer to 1, the more oval. All right, at the bottom, and we're just about done here. So we're starting with gravity. So gravity is the pull of the earth towards the sun. So it's an invisible force of attraction. Everything has gravity. Even you guys. Everything that has matter, so everything that has mass, has a force of attraction. But luckily for us, your gravity's not very strong and I'm not being pulled towards you. Any idea why I'm not being pulled towards you and I'm being pulled towards the earth instead?
That'd be going lower is the part.
Too complicated. What's the difference between you guys and the earth? Well, there's that. What? The earth has more mass. So gravity depends on 2 things. One would be the mass. And the other would be distance, because the sun has way more mass than the earth. But again, I'm not being pulled all the way towards the sun. I'm being pulled towards earth, and that's because I'm closer to earth. The larger the mass, the greater the gravitational attraction. And the closer the objects are together, the greater the attraction. Mm-hmm. All right, so because the earth is going around the sun in an oval shape. Now this, by the way, is an exaggerated version. When you look at earth going around the sun, it's actually much more circular than this picture right here. But because we are technically slightly closer to the sun during part of our orbit than we are during other parts, again, because it's an oval and we're at one of the foci, or the sun's at one of the foci, there are times in our trip around the sun when we're closer and times when we're further apart. Because we're closer sometimes, what would that say about gravity when we're closer?
Greater.
Yeah, so when we're closer, there's more gravity. Then when there is more pull on the earth, we actually end up moving faster. So when there's more gravity, we're actually moving at a faster speed. So here, when the earth is between C and D, the earth is actually moving slightly faster than when we're at A and B. And what that means is we can cover more ground. If you're moving faster, you'll go through the orbit a little bit faster. So when you're closer, we have a stronger gravitational attraction and we end up moving faster. So what we need to fill in here is between which two letters is the orbital speed the slowest? Which ones are we slowest between? Actually just A and B. That's when we're absolutely the farthest away. Here, we're getting closer. So you start from far, far, far away, and now we're getting closer as we go over here. So the slowest is going to be between A and B. And which two letters are we moving the fastest? That's between C and D. But if we were to figure out the area of these shaded areas, what do you guys know about area and two different triangle-ish shapes? Area and these two shaded spots. Area is the shaded area. What do they look like? Does one area look bigger than the other? Or do they look equal? Doesn't look equal? Doesn't look like that one's way longer, even though it's shorter. This one looks shorter, even though it's fatter. They're the same. The area covered's still the same. Even though this one is moving farther in its orbit, it has the same area. So the area covered from A to B and C to D are the same. And then finally, speed depends on distance from the sun. Then two vocab words that just describe locations on Earth, on our orbit. Perihelion is when we're closest to the sun. Aphelion is when we're farthest from the sun. You do need to know the difference between these. I've only ever come up with a couple goofy ones, but the aphelion starts with an A, so I always remind you, A, away. It's when we're far away. That's all I got. Technically, I also have ones, perihelions, you're with your parents. Aphelion, you're in apartment, which means you're far away from your parents. I don't know. It's kind of goofy, but you do need to know the different ones. Perihelion's when you're close to the sun. Aphelion's when you're far away from the sun. And then all we have left is practice. So I'm going to let you start your homework, which we're going to do just these 7 questions. Oh, I should point out one thing. On page 15, let's go to page 15 of your reference table before we do that. Page 15 of the reference table. We did already look at this reference table very briefly earlier this week. It is the solar system data that is for all the planets. We established that they do go from closest to the sun, Mercury, to farthest away, which is Neptune. We do have their period of revolution, so how long it takes them to revolve around the sun. We have the rotation. These, by the way, are in Earth days and Earth years. So when it says 243 days, that's how long it takes for Venus to rotate. That's 243 Earth days for it to rotate. Then they list the eccentricities here for each of the planets. So you can see that most of them are very small eccentricities. What does that mean about their shape if they're a small eccentricity? They're very circular, not a small orbit. Remember, eccentricity is describing, are they ovally or are they round? And the closer to 0, the more round they are. Also, as long as we're here, I'll finish this up. They do tell you how big each planet is in kilometers. And then they tell you mass, but these are in Earths. So you can see that Earth has a mass of 1. Mars has a mass of 0.11 Earths. Jupiter has a mass of 317.83 Earths. So it's really heavy. And then the densities are listed there. So you can notice a couple of the planets have a density less than water, so less than 1. So they're completely gaseous. So you have homework. How many people do not have access to a ruler at home? Or while they're wherever they're going to be doing their homework? So here's a copied ruler. So if you don't want to try and find a ruler when you get home to do your. So we're just doing questions 1 through 7. So what is that? Pages 15 and 16? All right, if anybody needs a ruler, you can grab one up here. Notes, 16, 17.